Hello everyone. In this video, we're going to work the 5 homework problems from homework number 10. I do want to draw your attention to some errors I saw in the work turned in, and these will come up in the different problems in the video. They involve how to start a subderivation, the use of free variables in sentences or lines on the proof, when not to use universal elimination, and then violations of the provisos on universal introduction and existential elimination. I will touch on those as we go. However, let me just comment briefly on the first one, how to start a subderivation. So let's suppose that we have to use a subderivation in our proof. I'm not going to use a realistic example here. You know that we have to make some kind of an assumption. Let's just call that P. And the subderivation has to have something going on down at the bottom of the subderivation so that we know when it's over. And that's going to be dictated by the rule. And then there's going to be a line that we add to the proof on the basis of this subderivation, right? So when I talk about how to start a subderivation, I'm talking about what exactly are we putting in this position. The annotation of the, basically the purpose of the subderivation. I just want to make clear, the only thing that can go in this position after we mark that the first line of the subderivation is an assumption, an auxiliary assumption. The only thing that can go in this place here in our annotation is a subderivation rule. And we don't have very many subderivation rules in our rule system. But let me just review what those are. So one of the subderivation rules is conditional introduction. That's a subderivation rule. And then another one would be the negation rules, negation introduction and negation elimination. We also have wedge elimination and biconditional introduction. And lastly, we have existential elimination. We don't have any other subderivation rules. So what makes these subderivation rules is that these rules take subderivations as input. So if you go back, open your book and look at each one of these rules, what you see is that along inside the rule statement is a subderivation. Okay, so what I'm saying is that the only way to annotate an auxiliary assumption for a subderivation is with one of these rules. Now, that rule is the rule that you're going to apply. I'm just going to use the same question mark here. It's the rule you're going to apply down after the subderivation is finished and you've moved to the next outer scope line, possibly the main scope line, possibly you're inside of another subderivation here. But that rule is intended to take this entire subderivation as input, okay? So when we annotate for a subderivation here, we cannot put something like universal elimination or conditional elimination or identity elimination or disjunction introduction or universal introduction or any of those other rules that simply take line numbers as input. Okay, so be very clear when you're starting your subderivations that you have in mind one of these rules that will actually take that entire subderivation as input when you come down to apply the rule, all right? So I think that I've seen enough cases where we have a rule statement here at the beginning of a subderivation, and sometimes that rule is the one that you wanted to apply. So you may say, well, I'm going to assume this for conditional elimination because I really want to apply conditional elimination next. Okay, that's not a good strategy. So you have to assume something. You're introducing a new line to your proof and a new scope line to your proof. And whenever you do that, you have to get out, right? So the goal of the derivation is always to get your target sentence along the main scope line. So if you introduce a new scope line, you have to have a plan for getting out, for stopping that scope line and moving to the next outer scope line. And that's a subderivation rule. It's a rule that will take this subderivation that you're putting together as input and let you stop the subderivation and put something new along the next outer scope line. Okay, so it's not too late to learn this. You need to focus on what are the subderivation rules in our system, right? And only use those when you're annotating an auxiliary assumption, and use them again at the bottom of the subderivation. Okay, I hope that at least those introductory remarks on how to start a subderivation are helpful. Keep your eye on the subderivations that I start in working these problems. I'll touch on the other three issues: free variables, using universal elimination appropriately, and the provisos on universal introduction and existential elimination as we go. Let's go ahead and get started on the first problem. So here's one approach to problem number one, and that's just to start incrementally replacing these names in a way that we're going to land on E all the way across. So the first thing we're going to do is take line 4 and replace those A's with C's. So F, C, C, D, C. That's 1 and 4 identity elimination. So we took 2 A's out of line 4 and replaced them with C because line 1 says A equals C. On line 6, what we're going to do is we take these 3 C's and replace them with D. So that will give us F, D, 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 D from 2 and 5 identity elimination. And then the last thing we're going to do is we're going to take all 4 of those D's and replace them with E because line 3 says D is the same as E. So that gives us F, E, 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 E from 3 and 6 identity elimination. I think that's the shortest proof, though there are many other ways to get the same result. Now let's turn to problem number 2, which I already have set up here with an overall strategy of existential elimination. So bringing this back to that point about how to start subderivations, notice that I have started a subderivation here, and it's a subderivation for existential elimination. That is one of our subderivation rules. I will draw your attention to the fact that I started that subderivation because that's the rule I want to apply. That's going to take this subderivation as input. The subderivation starts on line 4, and existential elimination requires a subderivation as input. So I'm planning ahead to use this subderivation for existential elimination. And that's what I mean by making sure that you're putting subderivation rules in here. Those are the ones those are the rules you're going to want to apply when the subderivation is finished. Okay, so let's also talk about those provisos on existential elimination. We don't want to violate them. So what you see here is that on line 4, RC ampersand MC is a substitution instance of line 3. So drop the quantifier, outer parentheses, replace the variable of quantification X with the name C. Okay, so I've got an instance of the existential generalization. That's just part of how to apply the rule for existential elimination. Also notice, I've flagged my subderivation with the name C, and that's because I want to keep the name C isolated to that subderivation. I don't want this name to have appeared above it, certainly not in the primary assumptions, certainly not in the existential generalization I'm working with, and also that name C is not allowed out, okay? So actually my target of this is going to be my target sentence, A equals B. This sentence doesn't have the name C in it, so it's allowed out. Otherwise, I would be violating a proviso on existential elimination. This is exactly the point where I was starting to see some free variables. So let me just erase those names there and show you what I mean. So let's say I just drop the quantifier and I have Rx and Mx. Those x's appear, they are variables, not names. W, X, Y, and Z are our language's variables. And these x's appear on a line without a quantifier. That means that they are free variables. So if I keep going, I've got Rx maybe by conjunction elimination. That's a free variable, all right? You know what a free variable looks like. It's a variable, w, x, y, or z, on a line that doesn't have a quantifier. Or in any case, it's outside the scope of a quantifier. That makes it a free variable. Those are not allowed in our proofs. They're not allowed in our language. So when you drop quantifiers, you got to replace those variables with names, okay? So too many free variables on homework number 10. So let's go ahead and finish this proof. Our goal is to get to the identity statement A equals B. So what we're going to do now is just break apart the conjunction on line 4. R, C, and MC comes from line 4, ampersand, E. Both of them come from line 4 by conjunction elimination. On lines 7 and 8, we're going to do universal elimination on lines 1 and 2. And it doesn't matter which one we go to first. What does matter is that when we drop these quantifiers, we replace the variables with a name. And in this case, we're going to instantiate to the name C, and you'll see why. If RC, then C equals A. And if MC, then C equals B. So 1 universal elimination and 2 universal elimination. Pretty easy to apply universal elimination. Just have to remember to replace those variables with names. And then what we're going to get next on 9 and 10 are actually 2 applications of conditional elimination. So we have if RC, then C is A on line 7. We have RC on line 5. That gives us C is A from 5 and 7. Conditional elimination. And then we have if MC, then C is B. And we have MC on line 6. That gives us C is B. So that's from 6 and 8, conditional elimination. Then our target sentence is actually on line 11. It's from 9 and 10. Identity elimination. Basically what's happened is we've taken the C out of line 10 and we put an A in for it. Okay, and we get to put an A in place of a C because C equals A. So line 10 is our context for substitution, and line 9 is our identity that justifies substitution. Line 9 says, take an A out of a sentence and put a C in for it, or take a C out of a sentence and put an A in for it. Well, we have a C on line 10. Let's put an A in for it. The result is A is B. And then on line 12, since A is B doesn't have this name C in it, which is the one that has to be isolated to the subderivation, we can move it out. So line 12 comes from 3 and 4 through 11 by existential elimination. Don't forget to cite that existential. Existential's up there on line 3. Subderivation starts on line 4 with an instance of that existential. And then the target sentence gets to come out because we've got everything together and we haven't violated any of the provisos. Okay, so that's problem number 2. Let's look next at problem number 3. So here, problem number 3 is started. I've got it kind of set up, and I'm actually, just a heads up, I'm going to go down a wrong path here for a few moments. So I have a plan to use existential elimination on line 2. I've started a subderivation with an instance, and notice I've annotated existential elimination there. It is a subderivation rule. It requires a subderivation as input, and that's the rule I'm going to apply to this subderivation. So when the subderivation's finished, I move to the next outer scope line. I'm going to apply existential elimination. Okay, so I'm going to take the sentence that's my target, which I hope to get inside the subderivation. I'm going to move it to the next outer scope line by existential elimination. How am I going to get it inside there? Well, I could get it by universal introduction on a sentence that looks kind of like this. And so let's take a look at how that might go. Suppose that I just take RA here off of line 3 by conjunction elimination. And then I do something creative like disjunction introduction, tilde LAN, wedge RA. That's from line 4, wedge introduction. And then I do implication. Actually, this takes me right down here, implication. So I drop the tilde and I turn the wedge into a horseshoe. That's implication on line 5, 5 implication. So looks like I'm almost there. So line 7 is clearly universal introduction on line 6. I take the A's out, I put X's in, and I add the universal quantifier. And then line 8 here, I'm home free. So my subderivation lasted from lines 3 all the way down to line 7. However, this is a misapplication of universal introduction. Universal introduction doesn't say you can take any name and replace it with a variable and add a quantifier. Universal introduction is very touchy. It has provisos. And the most important proviso is that we're not allowed to do universal introduction on a name that appears in an assumption. So there we have A's on line 3. And we just said, well, if it's true for A, it's true for everyone. And that's a violation. Line 6. That's a violation of universal introduction. So when you apply universal introduction, you need to do a check. You need to see whether the name you intend to replace with a universally bound variable appears in any live assumptions. That happened several times in the homework. But it's a very important proviso on universal introduction, so those all ended up being misapplications of the rule. So let's set this up again and try a different strategy. Okay, so let's look at this setup now. We have the same basic strategy, existential elimination, that's going to help us export this universal generalization along the main scope line. Universal generalization will be got by universal introduction on an instance. And let's look at this instance. If LBN, then RB. B does not appear in any of the assumptions, in the 2 primary assumptions, and not in the assumption for on line 3 for existential elimination. So those are the assumptions that are in charge or live when we get to this conditional. So we can do universal introduction on that name B. Now, how are we going to get this conditional? We're going to get it by conditional introduction. So again, we are assuming for horseshoe I, that is the rule we apply at the bottom of the subderivation after the scope line is finished. So those are the only kinds of rules we're going to annotate when we make an auxiliary assumption. We may have other plans for this sentence. We may want to add it to another sentence by conjunction introduction later on. We wouldn't put ampersand I here just because that's what we want to do with this sentence. We're annotating for the subderivation, not the very assumption that we're making. Okay, so now our goal is to get to RB. And here's how we're going to do it. Lines 5 and 6 are going to work on this universal generalization here, which is essential. We can't leave line 1 out of this proof. Many of you work this proof all the way through by working on existential elimination on line 2 and never applied a rule to line 1. That's an extremely unusual situation where we would have a totally idle primary assumption. So for all y, we can actually replace x with a or b, but we're going to replace it with a. It doesn't really matter. LAN ampersand LYN horseshoe a equals y, line 1 universal elimination. We're going to do universal elimination again right away. And this time we're replacing the y with b, LAN ampersand LBN horseshoe A is B. It's line 5, universal elimination. Line 7, we're going to start constructing the antecedent of this conditional in line 6. Notice we do have a conditional. So we want to put together its antecedent so we can take the identity statement off and use it. So what we're going to do is we're going to take LAN off of line 3 by conjunction elimination, and then immediately we're going to add it to line 4. LAN ampersand LBN from 4 and 7 ampersand I, conjunction introduction. That gives us line 9, A equals B. A equals B. So A equals B comes from 6 and 8. 6 and 8, it's an 8, horseshoe elimination, okay? Conditional elimination requires 2 line numbers as input. Make sure that you're citing 2 line numbers whenever you apply conditional elimination. Then what we have on line 10 is the other half of line 3, RA. Okay, so RA comes from line 3, ampersand elimination. Line 11 then, guess how we got it? We took our A and we replaced the A with B because line 9 says A equals B. So 9 and 10, identity elimination. The rest is simply annotation, 13 and 14. So line 12 comes from 4 through 11, conditional introduction. Okay, we started the assumption on line 4 as an assumption for conditional introduction because when we're finished with that subderivation, move to the next outer scope line, we apply the rule that takes 4 through 11 as input, and that's a subderivation rule. Then line 12 is a clean and, line 13 is a clean and legal application of universal introduction on line 12. The name B appears in no live assumptions. Obviously, the name B appears on line 4, but we're not applying universal introduction inside the subderivation. So we've got our universal generalization, and then we export it to the main scope line by existential elimination. Starting with the existential on line 2, don't forget to cite it, and then the subderivation that starts on 3 and runs to 13. Okay, so that's problem 3. Problem 4 is the problem that I got the most questions about before the due date. So I've got this one set up. As you can see, I've set it up for a negation proof. And here's a little bit why. Look up here at our target sentence. We're trying to prove that A does not equal B. And if we look at our primary assumptions, look through them very carefully, you see there is no identity statement in those primary assumptions. So this is one of those situations where we're trying to prove the negation of an identity statement. It's sometimes called a distinctness statement. A isn't equal to B, and we have nothing really to put that together with. So instead of constructing it or proving it directly, we're going to prove it indirectly. That's always a good strategy. If you can't prove something directly, prove it indirectly. And that means to use one of the negation rules, negation introduction or negation elimination. So I've got a subderivation for a negation rule, negation introduction in this case, because that slash through the identity sign is a negation sign. And that means that this rule that I'm annotating here on the right-hand side of my auxiliary assumption is the rule I'm going to apply at the bottom of the subderivation when the scope line stops and I move to the next outer scope line. So to prove that A is distinct from B indirectly, I assume that A is identical with B. And so that identity statement is going to play a role in our proof. Let's get moving with first applying universal elimination to line 1. We're going to instantiate to A because that'll give me a conditional, and FA will be the antecedent, and I have FA on the line by itself. So FA, horseshoe, there's a Y, G, Y, A. That's from line 1, universal elimination. Then on line 6, there's a Y, G, Y, A. That's from 2 and 5, 2 and 5, conditional elimination. On line 7, I'm going to change this A here to a B. There's a Y, G, Y, B. That's 4 and 6, identity elimination. And that's actually, that identity sign there on line 4 now has served its purpose. Why did I change the A to B? Because I'm looking up here at line 3, and I'm trying to put something together that looks like it. Actually, what I'm after is a sentence and its negation, right? because I'm doing an indirect proof. I'm looking for any sentence of the language and its negation. So there's a number of ways of getting it, but line 8, I'm going to instantiate line 3 to a name, and I'm going to choose carefully here. I'm not going to choose A or B, because I need to add a quantifier right back to when I do that. So let's go to C. So tilde GCB is line 3, universal elimination. And then on line 9, I'm going to add that quantifier right back, but it's going to be a Y quantifier. For all Y, G, Y, B. That's from 8, universal introduction. That's a legal move. I replaced C with a variable and added a quantifier. If you had put an A in there or a B in there and done universal introduction on it, you would be violating a proviso because the names A and B are in these assumptions, so we can't do universal introduction. So this was a strategic choice to choose the name C, okay? And that put me in a position to do universal introduction. And I have made a mistake here I need to fix. Please be patient. Tilde G Y B. I forgot the tilde. Okay, there's the tilde. So the reason that I did that is because when I do quantifier negation on it, I change the universal to existential, GYB. That's line 9, quantifier negation. And it gives me Q on line 7 and the negation of Q on line 10. Okay, so really what I needed to put the sentence and its negation together is I just needed to change the variable of quantification on line 3 from Z, okay, to Y. And then that lets me do quantifier negation to get the opposite of line 7, the explicit denial of line 7. That gives me a sentence and its negation. I can then stop my subderivation and move to the next outer scope line and apply a negation sign, in this case a slash, to my assumption, to the identity sign in my assumption up there on line 4. Okay, so just remember this tried and true strategy. If you're trying to prove something that you cannot prove directly, that means you can't piece it together from the little bits you've got to work with, then you need to try to prove it indirectly, okay? And I think that was probably where a lot of people struggled. That's a good, sound strategy, though, so you need to keep it in mind. Let's look at the last problem now. Problem 5 is our theorem. So as you see at the very bottom of the scope line, I have our theorem for all x, y, and z. If dx and x equals y and y equals z, then dz. We're going to get that by universal introduction in one of its instances. So here on the next to the last line, I have in place of those x's, I have the name a. I get that by universal introduction on one of its instances. So we've only got the z quantifier here, and in place of the y on the next to the last line, we have the name b. And we get that by universal introduction on one of its instances, which is just this simple material conditional. And in place of those z's, we have the name c. The conditional is going to be proven by conditional introduction. This is all very, very standard moves here. A conditional introduction, so we'll start a subderivation on line 1. We have the antecedent of the conditional as our auxiliary assumption. And we have the consequent of the conditional as the last line of the proof. Once again, I'll just point out the annotation up here. Conditional introduction is a subderivation rule. It is the rule that we're going to apply once the subderivation is finished, so that we take that subderivation as input for conditional introduction. And that's why we flag it here in the annotation. We're saying, starting an auxiliary assumption, starting a subderivation, it has an auxiliary assumption, and I plan to use conditional introduction to take this subderivation as input. So even though what I'm going to do with line 1 is conjunction elimination, I wouldn't put that as my annotation for this assumption. conjunction introduction is not a subderivation rule. It doesn't take a subderivation as input. So the first two things I'm going to do is break open the conjunction on line 1. Just go ahead and write down both conjuncts. There's dA. There's A equals B, and B equals C. Both of those come from line 1, ampersand E. Okay, the next two things I'm going to do on line 4 and 5 is break the conjunction here on line 3. So we get A equals B on a line by itself. We'll get B equals C on a line by itself. Okay, those both come from line 3, ampersand E. 3, ampersand E. And then on line 6, I'm going to get A equals C. So I take 4 and 5 together, A equals B, B equals C, therefore A equals C. That's from 4 and 5, identity elimination. And then DC, that comes from line 2, DA, and line 6, A equals C. So if DA and A equals C, then DC. So that's actually 2 and 6, identity elimination. So there's the subderivation. I got to my target sentence. I just need to tidy up my annotation. Subderivation runs from 1 through 7. Then I do universal elimination first on line 8, then on line 9, then on line 10, and that's it.